Hey friends, welcome to Chemistry Lover. You are watching Chemistry Lover, and I know you are preparing well for the upcoming NET exam, the December NET exam, and I am here to boost your preparation for the NET exam, right? So I got several requests for making videos on heterocyclic compounds, and I already made videos on the reactions of the heterocyclic compounds, but there is not much time left for making videos on the synthesis. But I will cover some of the important synthesis, and in this particular video I will be talking about the Knorr pyrrole synthesis, the synthesis of pyrrole, the method which is given by the scientist Knorr, and along with that I will solve a problem because there are several synthesis for pyrrole in your literature, in your textbooks, but all of them are not very important for competitive exams. But this Knorr synthesis is very important, and this particular problem I took from NET exam June 2015. So one specialty about June 2015 paper is that if you look at the paper, the questions are really difficult and it needs a lot of thought process. So that's why I want to cover most of the problems from that particular exam, because if you can think about that problem, other problems will be more easier for you. So that's all. So let's start today's topic. Okay, so as you can see, this is a problem given. Now if you know about the Knorr pyrrole synthesis, without doing any workout, you can easily predict that this will be your product. Okay, so here this will be your first product A. After that KOH is given, so what will be that step I will discuss later, but this will be your product, you can guess. But interestingly, in the question paper, the options where it is given, they have given the hydrolyzed product of one of the esters. So this option is given. So one remains as CO2 and one ester is hydrolyzed, and in other option this is given as it is, but it is hydrolyzed, and in another option both of them are hydrolyzed. So no product was there where two ester groups remain intact. So either one of the ester is hydrolyzed or another one is hydrolyzed, or both. So the main problem here is you have to predict, or you have to elucidate that which ester will be hydrolyzed, and that's why I picked this problem. Okay, so and for predicting that you have to do the workout of the mechanism, because if you don't do the workout, the mechanism, you cannot predict which ester group will be hydrolyzed. So let us first look at the reactive functional groups in these two molecules. So both of these molecules, they contain several functional groups, the carbonyl functional group, the NH2 group, and so on. Now there are several possibilities of reaction. As base is given here, you may think about the hydrolysis of this ester group in the first step. That may be one reaction, or you may also think about Claisen ester condensation, aldol condensation, and several other reactions. But let me tell you that if you have amine group, for example here the primary amine group is there, and some ketone or aldehyde group, the reaction which is most feasible, or the reaction which will occur 100% is that the condensation reaction that will give you the Schiff base. So when you see any amine and a carbonyl functionality group, now that carbonyl functionality group should be ketone or aldehyde, not ester, right? So here you have a ketone group, here you have a amine. So the first reaction which should come in your mind is the condensation reaction to give you the Schiff base or the imine. So here we will get this Schiff base. So in the first step we will get this Schiff base, right? So this is the first step of the Knorr pyrrole synthesis, and it is a prototype reaction. In every case this will happen. Now you know that this iminium ion is not that much stable, and if it has alpha hydrogen, it will rearrange to enamine, right? So you will have NH, sorry, here you will have NH, and here you have this CO2 group. and now here you have this carbonyl group. So this will form first. Now let us look at the reactivity of these two ester. Okay, so if I open this structure of this ester, it will look like this, and same for this. So here it will look like this. Now although both are the ester group, but their chemical environment are not same. Why? Because you can see, you can push a lone pair like this into this ester, so it will have a resonating structure like this, OAT, and here you will have NH plus and this, right? So this, but you cannot push a same type of arrow into this ester group. So this ester group is not in conjugation with this nitrogen lone pair, whereas this ester group is in conjugation with this nitrogen lone pair. Now this electron donation from this nitrogen lone pair to this ester group makes this center electron rich. Okay, so this center is electron rich, whereas this center is relatively electron deficient, and its electron deficiency is even increased by the presence of this alpha carbon, because you can see there is a positive charge and it will withdraw electron from here, and this in turn withdraw electron from here. So this center is electron poor or electron deficient, right? So this is electron rich, this is electron deficient. Now here you are using aqueous KOH and room temperature is given. So this is not a very drastic condition. We can consider it as a mild condition. And in mild condition, ester hydrolysis can only occur if your ester is very much reactive. If it is electron poor, if you have electron rich ester, that will not be hydrolyzed in mild condition. So in this mild condition, only this ester should be hydrolyzed. So if this ester is hydrolyzed, what you will get? So this ester will be intact, but you will have the hydrolysis of the other ester group. So here you have this keto group, and now this ester group will be hydrolyzed to give you the carboxylic acid. So this ester is hydrolyzed to this carboxylic acid. Now the usual reaction step of Knorr synthesis. So now this enamine will react in a typical pathway to give you this 5-membered ring over here. So here you will get this 5-membered ring, and here you can see this acid group will be there, and now this ester group will be there. Okay, so here you have this OH and this methyl group, and this, now you have this positive charge over here. So now here you have another hydrogen. So basically protonation can occur here, and this OH can go. So you will get, so this step, I am just writing this mechanism very casually. Several book write down several type of mechanism, that doesn't matter. Okay, so here you have this acid group, now double bond here. Now you have proton over here, so this proton can go, and you will get your product like this. So here you have this CO2 group, here you have this CO2H group, and this. So this is your pyrrole, right? So this is the answer. So this is product A. Okay, so in product A, only one ester group is hydrolyzed, and that is adjacent to this nitrogen. So this ester group will remain intact, only this ester group is hydrolyzed. Now let me erase it. Now on product A, they are doing reflux with KOH, right? So now if we do reflux with KOH, now this is refluxing condition, and here again you can argue that okay, this ester group is still in conjugation with this, but you can see this is a aromatic compound, and this nitrogen lone pair is already delocalized into this group. It is already delocalized into this group, and also it is delocalized into this acid group also, right? So you can also push arrow like this. So it is also delocalized into this acid group. So the delocalization of this nitrogen lone pair into this ester group is much less compared to the previous case, where it was only delocalized into this ester group, but now it's the lone pair is shared into this aromatic ring, into this acid group, and then into this ester group. So here the delocalization is much less. So that's why this nitrogen, this carbon center will not be that much electron rich. At the same time, you are using the refluxing condition. Previously it was room temperature, so at that time the reaction condition was mild, but now it is refluxing condition, so it is a pretty harsh condition, and at this condition hydrolysis can occur also on this ester group. So if this hydrolysis occurs, you will get acid group over here. Okay, so now both are acid. Now heating, so reflux means heating, and in the final product they have given the options like the decarboxylated product. Okay, now the question is which ester group, which acid group will undergo the decarboxylation reaction. Okay, now here, so I already, when I discussed the reactivity of pyrrole, I told you that the reaction of pyrrole, the electrophilic attack by pyrrole always occurs like this. So with full conjugation, right? So it will always react from this 4 position or from this 2 position, not from 3. Sorry, this is 1, 2, 3, 4. So this is 4, this is 5, right? So from this 5 position or 2 position, not from this 3 or 4 position, because if it reacts from 3 or 4 position, then full conjugation is not involved, right? So that's why it will try to react from this 5th position. So if it reacts from here, so now we can write like this. So it can take this proton from here, so that will give you so here I write down just like this. Now you will have this intermediate where you have O minus over here, you have plus, right? Now this O minus can push and it can go like this. Okay, so this is how you will have hydrolysis of this ester and you will get this product. So this acid group will remain intact, only this acid group is decarboxylated, and you will get this product. So this is your product A and this is your product B. So this question involves lot of concepts, okay, and by solving this question you will revise a lot of your concepts regarding reactivity, and that's why I picked up this problem. So hope you enjoyed the problem, and thank you for watching.